Okay, so let's see. This is a picture of the distribution of galaxies on the celestial sphere as it was known in about 1970 or 75 or something like that. And it represents the entire sky. So this is like a Mercator projection, where the Milky Way is the great circle, or the plane of the Milky Way is running around the equator, so it's what we call galactic coordinates as opposed to equatorial coordinates. And the reason you don't see any little black dots there is simply because the Milky Way has dust between the stars, and dust absorbs light. We can't see very clearly the outside universe beyond the Milky Way in this particular direction. So you're supposed to discount the fact that there are no black dots there. Otherwise, there are something like 30,000 galaxies represented here. So it's a map of all galaxies brighter than the sun limit, which corresponds to some particular distance, more or less. And what you're supposed to see is that there is a decidedly non-uniform distribution of galaxies. In other words, galaxies clustered. There are some regions where there are dense, large blobs, sort of large amounts of mass of galaxies is there, and other places where there are holes. And this is a two-dimensional map. So what we're seeing is a lumpy distribution of light from galaxies or clusters of galaxies projected onto the plane of the sky, which means that the actual lumpiness will be greater than what you see here. The projection can only smooth things out. So this is fine. I mean, we know that gravity makes things clump together, or we see star clusters. After all, why shouldn't there be galaxy clusters? And the very, very deep and intriguing intellectual point is that some of these structures, like this one here or this one here, are so large that there has not been time enough in the age of the universe for gravity to pull these things together as structures. So the most logical recourse, if gravity has not had time to make these things, then they must be primordial. The structure must have been built in at the beginning of the universe. So that is the fundamental connection between what is the buzzword is large-scale structure, okay? Large-scale structure in the distribution of galaxies and cosmology. And so those are the fields that are coming together or have been coming together for the last 10 or 20 years or so. So what the Sloan Digital Sky Survey is all about is an effort to make a definitive map of this, a modern map of the distribution of galaxies in order to make a precision test of cosmological models. So let me show you the connection between a cosmological model, and maybe this is a good time for me to show myself. So this is a simulation which is a computer code which tries to put in all the physics of how matter in the universe has developed. So what you're seeing here is a slice of the universe which is many hundreds of millions of light years on the side at an age of 1.6 billion years after the Big Bang. And as I go through this, you should see that things are starting to cluster, or I should say that the lumps of density are becoming enhanced as matter moves in to the high-density spots and away from the low-density spots. So now we're at an age of 6 million years after the Big Bang, and you're starting to see cusps. These are the things that will turn into the clusters of galaxies. So, in other words, let me try to give you a little bit of a scale here. The Milky Way is maybe 100 times its own diameter away from the Andromeda Nebula, which is a galaxy like the Milky Way. So that defines the local group of galaxies. So if you think of the Milky Way and multiply by 100, that's roughly the size of a group or a cluster of galaxies. Okay, that's on this scale. That's bad. Okay, so this is a huge chunk of space compared to the sort of familiar things like the Milky Way. And here we are at 13.5 million years. Okay, so let me run through that again just so you get a sense of it. So this is a two-dimensional map of the present day universe. Here's the early universe. Here's structure developing to the present day. Okay? So this is a particular model, And if you ask what are the things that you would have to put into that model to make that calculation, here are some of the things. You need the age of the universe. Okay? So we don't know that to high precision, but that's the number that we need to put in. We need to put in how much ordinary matter there is, that is to say, protons and neutrons. And that is, of course, that makes sense because the more matter, the more gravity, the more stuff will come together. However, we know that there's a lot of stuff other than protons and neutrons. So we call that dark matter, or just to say, using the word exotic here, meaning it's not protons and neutrons. And that is actually dominant. There's much more of that stuff than there is of ordinary matter. So we need to know how much of that is, because it also gravitates. So we need to know how much there is. That was the story about 5 years ago. I could have stopped there. But unfortunately, it gets worse. So not only do we not know how much, we don't know what this other stuff is, but it turns out that the dynamics of the expansion of the universe is dominated by something that isn't even gravity. And for lack of a better word, we call it dark energy, which explains nothing. It's just a label, but there's something out there which is not gravity. Then we have to explain, we have to put into our model the distribution of density lumps. Right? Remember I said that they had to be primordial, they had to be built in the beginning. So you have to specify a recipe for what that would be. And then finally, we don't actually see the mass. What we see is the light that is and the light and the mass might not be relate to each other in one way. So this is a list of ingredients. And the point is that if we make the observations, we might be able to sort of reverse engineer and figure out what some of these things are by comparison of model with respect to the data.
I got a question.
Yeah.
On the slides before this, when you went from way back to current,
yes.
You know, you got more and more structure. So
right.
when you look out further and further away, there's
yeah.
less structure that you see.
Yes.
And so, like, we see more structure in let's say a billion light years around us than we would if we looked out 13.
That's correct. That's correct. Right. So what this map is here is by ordinary standards would be extremely distant galaxies, but by the standards of that little movie I showed you, the time scale, that would be the most recent slice. So none of these galaxies are more than a billion light years away, which means that if the age of the universe is 13 and a half now, this would be a slice of 12.5, that would be 1 billion years ago. Right? So these are local. If we were to use the very large telescopes available to us now and see very distant galaxies, then we would in fact be able to look at those other slices, and that is in fact a very high priority.
And so in a Mercator map like this, if you went back 12 billion, this would be more uniform than what we see.
Yes. Yes. So studying the evolution of this is another very powerful constraint, and we're trying to do that.
When we talk about things that evolve over this huge scale of time, is there any consideration given to the lifespan of a galaxy?
Yes. The galaxies are made out of stars. Stars change with time, and therefore we expect the galaxy to change with time. And so, indeed, this last point here, for example, if the light is changing, how mass is traced by the light could also change. And so you're starting to appreciate the complexity of this, that nothing is easy, and we need to sort of tease out how all of these things are working. That's not a very deep answer to your question. I guess the right answer would be if there was some way to measure the mass itself directly in situ, for example, by doing orbit analysis at early epochs, then that would be the ideal situation. And there are ways to do that, like measuring how fast galaxies are spinning. Okay, the S is for the Sloan Foundation, who is a major sponsor for the project, the Sloan Digital Sky Survey. We also have funding from NSF, from NASA, from the Department of Energy, and bunch of institutions that I'll show on the next slide. But this is our observatory on Apache Point, which is in, I guess I'm getting ahead of myself. There's another slide which explains all this stuff. But here's the motivation. Create a three-dimensional map, not the map projection, but actually measure distances to these galaxies with a three-dimensional map. Blah, blah, blah. Do it in several colors and measure the spectra. We'll talk about that.
Are you doing anything south of the celestial equator with that?
Yes. This is the northern galactic cap. So this is in galactic coordinates.
Okay.
So it would be the top half of the first slide. And that turns out to dip below the celestial equator. So we're not going too far below the celestial equator. Here's a whole bunch of institutions. Yeah, right. So that's the obligatory slide. So everybody's happy. We have built everything from scratch to do this one project. So it wasn't, oh yeah, here's a telescope, maybe we can get some time on this telescope. It turned out that in order to do this project, the project is absolutely huge. We'll produce something like 30 terabytes of data with that at the end of the survey. And it's bigger than the genome project in terms of data. It's something. So to do that, we had to build a survey, a telescope that would do nothing but this survey, cameras that would do nothing but the survey, and a data system that was designed absolutely for the survey.
I have a question.
Yeah.
I was wondering about the exotic-looking construction of that tube, the
Yeah.
gray bars, and so what is the function of all of this?
Well, we would not do this again if we had the books. At the time, we thought it was a good idea. Let's see if I get a. Let me go forward here and see if I can better picture that telescope. Probably not. Well, let's go back. Oops, sorry. Not very good at this. Okay, this is actually a better view. This is a roll-off shed. So that this whole building is on tracks, and it runs. The tracks are right here. And when the telescope is pointed to the horizon, the building can roll over the telescope. Okay? So we thought that this was a good idea because the cost of buildings like this is a function of its volume. So the smaller the volume, the closer it can fit over the telescope, the better in terms of cost. The other thing it does is this over here is west. In fact, that's White Sands National Monument out there. So this is in southern New Mexico looking north, so this is west. The prevailing winds come up the mountain range like this. So by putting the telescope on a concrete pier over the edge of the mountain, that's about as, you can't do any better than that in terms of being in the prevailing wind. And that has the beneficial effect of having the steadiest airflow, and therefore the best image quality. The image is not affected by the oiling in the atmosphere. By moving the building away, we have the smallest amount of metal that could radiate heat into the night air around the telescope. So all that was theoretically great, right? In fact, this has been a real pain to do this for all kinds of reasons. One is that you can't work on the telescope in the daytime without pulling the building off, and you can't do that if it's raining. So if it's raining in the daytime, you can't service the telescope. That's only the smallest part of the problem. Anyway, to answer your question, the penalty you pay for not having a building is now your optics and the telescope are subject to being illuminated by any light around it and any wind that's around. So this thing, this box here, is separately mounted. It does not touch the telescope. This is a completely separate mechanical thing, which serves as a wind buffer, wind baffle, and a light baffle for the telescope. So it's a very bizarre. I mean, it does work, but we just wouldn't do it this way again.
What part of the spectrum are you doing? I mean, the visible, but are you doing any IR or UV with it too?
No, it's just it's the entire optical range, but only the optical range.
Okay.
This is for, I was saying to some people earlier that this slideshow is partly for some amateur astronomers, so I threw some things in here that I thought would appeal. transducers. I won't belabor that now. This picture will explain a little bit about how the color images are made and how the camera works. So if you can understand this picture, you understand how the survey works. This is an asteroid, okay? And we have 5 different filters in this camera. And the way it works is that the charge is essentially we don't take snapshots, we don't take exposures. Everything is done electronically. As the telescope, let's say, is pointed in this direction, and as the Earth rotates, the images drift across the back of the focus of the telescope. And at the very same rate that the Earth is rotating, we electronically move the charge, the electrons that are being liberated inside the pixels of the CCD camera at exactly the same rate. So we shift everything at the rate that the Earth is rotating. So there isn't any mechanical motion at all. There's no shutter, there's nothing. And it's just, so the data come out as one long stream for each detector. But there are 5 filters. So let's say that this is the drift rate. So I go through the red filter, then the infrared filter. This is infrared in the sense of our nomenclature. It's not really thermal infrared. Ultraviolet, Z is another infrared filter, and the green band. And so and there's about a minute across each of these filters. Okay? So there are roughly 5 minutes or so from top to bottom. Okay, so we get this. So we get 5 long strips, 1 in each filter for each column, and then we multiply that by 6 to get the whole thing. So this is a data set from 1 scan across the sky as the Earth rotates. Notice that there will be gaps in here, and we fill those gaps by the next night. We point the telescope to the same location, except shifting a little bit, so that now the detectors will go down and fill in the gaps. So we need two passes to get a scan that has no gaps.
Okay, so the telescope isn't doing any mechanical tracking at all.
Now, I said what I said to make it a little bit clearer how it works, but in fact, we have to scan on great circles because the field of view is so large, it's about 3 degrees or 2.5 degrees, let's say, from this side to that side, that if you did anything but scan on a great circle, there'd be a different scan rate at the top on one edge than on the other edge. So we could park the telescope and literally lock it down on the celestial equator, which is a great circle. But as we move away from the equator, we have to actually move the telescope a little bit. And so, in fact, there is some mechanical motion.
Yeah.
But
now, is that an L-azimuth mount?
yes.
So you got to do a differential rotation and all that
It's
stuff.
yeah, and you have to rotate the camera, really, which is what I think is. Yeah, that's right. So it's a little bit complicated. Okay. So we make color pictures like this, and we do it. So we have 5 filters. Of the 5 filters, we choose the 3 that are in the middle of the spectrum, so blue, green, and red, more or less. And this will show you that as the asteroid came in, let's see, this would be. I will confuse you if I told you what the real filter was. It's actually green. Okay, but never mind, it doesn't matter. And then those are the 2 filters that are missing, and these are the 2 filters that it came out at the end. Okay? So this is how we can find asteroids, by the way. This is just a picture of another chunk of data. We call it a frame. It's a 3D color edition, like I just told you. It's a cluster of galaxies. And as such, this wouldn't look particularly special. It looks like any picture in a textbook of a cluster of galaxies, right? So why is this a big deal? Well, here's why it's a big deal. These are the 6 columns from one scan and the 6 columns from the next scan spliced together. Now, we actually don't have white columns between them. I'm only having it here to show you that they are spliced together. But the actual data doesn't have white stripes. That thing I just showed you was about this size. Okay? It's one chunk of one of the stripes. So that alone is so the point is that, and this is only a few minutes of data. So for a night, the actual size of our image would be about 8,000 tons. See, no, I'm sorry. There would be 8,000 of these guys would make a night's worth of data. Okay, and about 500 of these or something like that. So the images are absolutely enormous, and they're so enormous it's hard to show them, right? Because if I were to take it and squeeze it down, you wouldn't be able to see, it wouldn't look like anything. So this is very recent. We got this just a couple of months ago. You may recognize this as the Andromeda Nebula. Okay, so you've seen pictures of this before. You can see that we're still not getting our processing software quite tweaked up for this. We never intended to scan something like this. And it looks like a picture of the Andromeda Nebula. However, each one of these rows has 2,000 pixels. So I've already scrunched it down enormously. You can't possibly. In other words, this display is probably 2,000, no, not even that. It's about 1,000 pixels. I can't show you more than 1,000 individual pieces of information left to right. And in fact, each one of these is 2,000. And I'm not even showing you the whole thing because this is 7, if you count them, and there are 12. And then this whole thing goes 10 times that dimension either direction. And that was only 3 hours of work to do that. Yes?
I'd love to see this set up like in an IMAX movie theater. Something where you could have film big enough where you could actually put most of the resolution on it, and a surface big enough where it's your whole peripheral vision.
Right. Yeah. That would be one way to kind of try to get the enormity of the image across. Right. Yeah.
Is the non-uniformity of the strips due to dragging the camera, the CCD?
I don't think so. I think it has to do with the software for determining the background level is keying on some of this, and we haven't got that quite right yet. But that we can do that with the post processing. Okay, I want to make sure I don't go over, so I can speed up or slow down and sort of see how it goes. This is just to remind myself to say that the data are processed in Fermilab in Batavia, Illinois. This is a picture of Fermilab. The buffalo are out here. Okay. So Fermilab is, of course, an accelerator laboratory, but like many of the national laboratories have sort of small programs in other branches of physics. And for some interesting historical reasons, Fermilab has had a cosmology group. And so it was natural because of the computing power there for the high-energy physics experiments, plus the theoretical cosmology interests to have the processing of the Sloan digital survey be done here.
Are they keeping up with the amount of data?
Yes. So we're very pleased that a night's worth of data, we actually sent tapes by the Federal Express from New Mexico to Batavia, Illinois. That's how we move our data. And they arrive and they go into this building here, the Feynman Computing Center, and in a few days we have the data processed for that night. We also take spectra, and you'll hear more about that this afternoon, where we're going to do a project on measuring redshifts. Okay, so we'll be looking at spectra. And the key thing, so now I'm on a totally new topic. Okay, so on one hand, the telescope has a camera which takes these beautiful and huge pictures. On the other hand, the telescope also has another instrument, a spectrograph, which is similarly large in scope. Since there are 2 of them, there are 640 spectra that are obtained all at the same time, but we get about 1 an hour or so. So that means that in a night we get roughly 8 times 600 spectra. Okay, so that's a huge throughput of obtaining spectra of astronomical sources. Okay. Do you know what a redshift is? Okay, you're going to be measuring those this afternoon. So we measure redshifts, what type of spectrum it is, and once you have a spectrum, you can measure, for example, say a star. I'm getting ahead a little bit, but just to bring you up to speed. If you have a spectrum star, you can measure its surface gravity, you can measure its temperature, you can measure its pressure, and you can measure the chemical abundance of the light at the surface coming off the surface of the star. So you get a huge amount, plus the velocity of the star, how fast the star is rotating, what the magnetic fields might be, an enormous amount of information about the physics of the star. And similarly for other astronomical sources. So we're powerfully motivated to get a spectrum.
Okay, the distribution of galaxies isn't exactly all perfect on your imaging, so do you have to move the fiber optics around to get spectra-specific galaxies?
That's what this thing is. So if you look at this, it's maybe not very clear from where you're sitting, but this is a plate, a metal plate with has holes in it that are drilled to the exact locations of where we know the galaxies are because we have the images of galaxies.
Okay.
So we do the imaging first, we do the astrometry to measure the exact locations of the galaxies. And we have an automated drilling machine.
CNC.
CNC. And then this is archaic. We have a human being putting these fibers into the holes. And we chose that route because we knew how to do that. We knew how to, and we have not regretted that decision. We think that not building a robot was a good idea. This is another picture for the benefit of the amateur astronomers that shows the back end of the telescope. So the telescope is pointing that way from right to left. We're looking at the bottom of the telescope, and my joke is it's like opening in the hood of your car. You see a lot of hoses, and it's very difficult to figure out what it is that you're looking at. And it's not important. It's just, that's what a modern telescope looks like. It's a mess. Okay, this is actually an important slide. It shows a combination of imaging data and spectroscopic data for the same objects. So down this column here, you have some not very good images of galaxies, but you may be familiar with the Hubble classification scheme for galaxies. The ellipticals are one extreme, and the spirals, different types of spiral galaxies, that familiar to you. But that's more or less what this idea is. Here's an elliptical galaxy. Here's a spiral galaxy with a larger bulge. Here's a spiral galaxy with a smaller bulge. And this is supposed to be some kind of sequence of morphological types of galaxies. And this is the spectrum of that galaxy. That's the spectrum of that galaxy, and so on. And what you should see here, first of all, is that these dips, the absorption lines, aren't exactly in the same place. This one is a little to the right of that, and that's a little to the right of that. And that's because these have different redshifts. So, of course, the spectral features will be in slightly different places. And then you can see that they have the redshift, the symbol for redshift is Z, and they're a little different. But never mind that for the moment. If you just look at what the shapes of these spectra look like, you can see that there is also a sequence going from top to bottom. And these are kind of, the energy is there's kind of a concave to the right kind of effect, and here is more flat. And down here we're starting to get emission lines as opposed to absorption lines. And so this is a signature of hot stars that are making gas around them fluoresce. So this is actually from the interstellar medium in the galaxies. And this, as opposed to the flat stuff, which is from the stars that are in the galaxy. So we're seeing a combination of starlight and light from gas. So what this says is that there's a correspondence between the type of light coming out of galaxies and what their shape is. And that is a very, very basic element of extragalactic astronomy that we still don't really understand. We'd love to know why, we know have all kinds of ideas, but I think it's fair to say we don't really have a deep understanding of why it is that that's the case. All right. You may have seen pictures a little bit like this. This might be, in fact, slightly reminiscent of my movie of the theoretical structured development. This is the three-dimensional map. It's very hard to show a three-dimensional map on a flat screen. So this is a single slice through a three-dimensional volume. It's missing data here because that's the direction of the Milky Way. And this coordinate is distance. Okay, so we are here. That's us at Apache Point in New Mexico. So for any galaxy, we plot it first of all in the radial direction by its distance, which we know from measuring its redshift, because of the expansion of the universe. Is that okay, that concept? Okay, all right, good. And we, of course, know where it is on the sky, so we can plot its angle. So this allows us, this is just one slice through a three-dimensional line. And we can compare these data with respect to models. Okay? And then total, in terms of distance, the most distant galaxies out here would be 1 or 2 billion light years away. So not that far. As opposed to this plot, where the previous plot was right down in here. Okay? So this gives a lot, it's not very impressive on this display, but we are measuring, we can use the color maps to select galaxies that are likely, oh hi Chris, we'll pause while our Fermi Lab group arrives. Do we have enough chairs?
Yes, we do.
Okay.
Hi, sorry.
How well is this statistical plumbing match with the agents that we need?
I hope you have a slide that shows something like that. Yeah. And Sanjay, I can ask, well, how long should we go for?
It's up to you.
Okay.
We are flexible.
Okay, all right.
So this was like
Yeah.
your sequential slides where
Yeah.
the further up you go,
Yeah.
the more uniformly distribution it is. And the
Okay.
and
Yeah.
the closer
Yeah.
you are, the more complicated.
Okay, all right. So this is a bit of a cheat here, and I'll explain why. But first of all, let me tell you what this is a map of. With the maps, the color maps, the imaging scanning that we have, we actually know an awful lot about each galaxy. We know how bright it is, we know how big it is, we know what its color is, and that's enough information, and morphological type. That's enough information to get a pretty good idea of how far away it is. And so we can pre-select those galaxies that are most likely to be in this nice homogeneous category that we call luminous red galaxies. And that is what we're plotting here. So these are the galaxies that allow us to go out farther because they're in fact more luminous. We can see them to greater distances. So this is a way to extend the reach of this survey here to much higher distance. Now, as you pointed out, it looks like, it may look like, that it's sort of getting a little bit more uniform out here. But that's not actually the case. I mean, it's not immediately, obviously, the case without doing the analysis correctly. Because what is really happening is that as things are farther away, they're fainter, and we start to get to the edge of our detection limit. And so they're getting fewer galaxies out there. You know, there are fewer galaxies out here than here. They're not really fewer galaxies. They're only fewer galaxies in our data set. Okay? And so because of that fall off of numbers of galaxies, it may look to you like it's getting more uniform. But that effect should happen way out here. No, we're not there yet. It should happen, but it's not there. This is a theoretical model that's supposed to look qualitatively like this. And so you're saying we're sort of on, and the point of this plot is to show you we're sort of on the right track, I think. It's looking about right. Okay, this I won't belabor, but this is the kind of plot that astronomers actually look at. Okay, it's all very well to look at those plots and say, well, we're sort of on the right track, it looks about right, but we'd like to do a better job of quantifying the information that's in the clumping information. So this is what's called a correlation function. Okay, it's basically you ask for each galaxy how well correlated are the galaxies around it. Okay, so if you think of things in a hierarchical sense, in other words, if you have groups and then you have groups of groups and then groups of groups of groups, then you would expect that the shorter the distance between two galaxies, the higher the correlation. And the larger the distance, the less correlated things will be. So that's essentially what we're measuring here, is the degree of the correlation function versus distance. And this MPC is a megaparsec. A megaparsec is 300 million light years. Okay, so this is 300 million light years. That's 3,000. That's 3 million. Oh, sorry. This is 3 million light years. This is 30 million light years, and that's 300 million light years. And these are for different types of galaxies: red galaxies, blue galaxies, and everything combined. What it says is that the blue galaxies, the ones with the emission lines and the hot stars, cluster in a different way. This is also a very important thing, because remember what I said at the beginning about we want to know how light and mass are connected. If different types of galaxies cluster in different ways, then that's direct evidence that there is no, that we can't just take this at face value, that we have to understand what's going on here, and we don't understand what's going on here. Okay, let me talk a little bit about quasars now. So everything I said so far has to do with galaxies. We're also doing a survey for quasars, and Cristobal, who just came in, will tell you more about the quasar survey, or the quasar spectrum this afternoon. For now, let's think of the quasars as being things that are so luminous we can see them at even farther distances from the galaxies. So we can think of those quasars allowing us to look at the fringe of the universe, as it were. So we have to find them first. And the problem is that they look like stars. You look at an image of a quasar, it looks just like a star. So we have to figure out a clever way not to put get spectra of uninteresting things to us, namely the stars. It turns out that if we make a diagram like this, which plots the ratio of the light between two of our filters versus two other filters, that the quasars are distinguished from the stars. So these black dots here are stars. And essentially, it's a sequence of temperature. These are, sorry, I didn't explain very well. The lower left is blue, upper right is red. Okay? So if you were to plot a light bulb, the position of a light bulb on this plot, the light bulb would either be up here or down there, depending on what the temperature of the filament was. Or vice versa, you could determine the temperature of the filament by where the color of the filament was on this plot. So these are hot stars, those are cool stars. And there are stars. You can tell that from this data.
Yeah. The left to right axis is temperature, and the vertical axis is pressure.
They're both a measurement of, think of it this way, if you knew that the thing was a thermal object, like the sun or a light bulb filament, then you'd only need one of these, one color would suffice. The other color will tell you that it is a thermal object. It gives you enough, it's a constraint, so it has to match both to be a thermal object.
So black bodies would be at the 45-degree angle?
Yeah, more or less. And so stars are not perfect black bodies, but they're pretty close to black bodies. Whereas quasars are not. They're very different, and we can tell. And the whole point of this diagram is to say we measure things we call colors, which is the ratio of the brightnesses between the two different filters. And from the colors, we can tell if it's a star or if it's not a star. We don't do that with 100% accuracy, but we do pretty well. So here is the kind of data that you'll be looking at this afternoon. These are the images of the quasars. It looks like a star, very uninteresting. Here's another quasar. It looks like a star, very uninteresting. That is the redshift, 2.2 and then 2.3. Okay, the redshift, as you recall, is related to distance as a measure of the distance. Let's see if I can go back here just. Okay, so remember 2.2 or 2.3 as opposed to 0.2. See, so these things are 10 times the redshift of stars, and so of galaxies, and therefore they're much farther away. They're correspondingly farther away. So we look at and we see a very different kind of spectrum than we saw for the galaxies. Instead of the sharp absorption lines and the sharp emission lines, we see very broad emission lines. But I don't want to steal Cristobal's talk, so I won't say too much about this. But this is, I will say that this gives you a sense of what our software does. Our software goes in and does automatic pattern recognition and determines what element created which line. And that's what tells us which. This is the redshift plot for the quasars. And you see it goes out to, now our highest redshift now is 6.4. It's a new discovery that has not actually been announced formally yet. But we have a few way out here. Those correspond to things that are less than a billion. They were formed, and the light that we are now receiving in our telescopes left the quasar less than a billion years after the Big Bang. Or to put it differently, we're looking back to the Big Bang about 93 or 94% of the way to the Big Bang. That gives you a sense of how far back we're seeing. This was a slide was made before our recent discovery of the 6.4 object. This is the previous record was 6.2, and it shows up as a miserable red dot. Okay, you can just barely see. And that was a credit to the accuracy of our software to find this thing, because this little red dot could have been any kind of a flaw that you could imagine. And so you have to have very good software to be able to find these things. I've not made myself very clear about this. These you might ask, why? Let me back up 2 steps. The telescope we're using is a relatively small telescope. It's not a big telescope by the current standards of business. What we do is to cover a huge area of sky, huge amounts of square degrees of sky. And the smaller telescope is ideally suited to do that. So you might ask, why is it that a relatively small telescope is capable of finding the most distant known objects that anyone has ever seen? And the answer is a little bit complicated. It has to do with the kind of the balance between the rarity of something which is incredibly luminous and therefore visible at great distance, but you have to cover a huge amount of sky to find it. Okay, and it turns out that wins. So that means that a wide-angle telescope is a better way to discover the most luminous things in the universe.
So now that you know where that is, you can point your Keck or something.
Yes, absolutely. That's exactly what we do. Yeah. So there's a signal that says go Keck, go look at it. Exactly right. Okay, so we have to have really good software to sort through the chaff, and we probably looked at probably something like many tens of millions of images to find this one object. And that has, so if you imagine if your error rate is one error in 10,000, that's nowhere near good enough, right? You can't possibly do it like that. Okay, this is the most recent thing, which, as I said, is just brand, this is sort of months old. What this shows is the spectrum, which you'll see again a lot more of these this afternoon. The spectrum is the amount of energy or the amount of light, the intensity of light on the y-axis, and the wavelength on the x-axis. And this is sort of thing astronomers love. I mean, it just go this wonderful stuff here. And the important thing here is the absence of anything right here. So this is absolutely zero. This is in fact taken with the Keck spectrum in very bad conditions, by the way. We have 2 nights ago we got a much better spectrum with the Keck. And this says that this is actually a measurement of the opacity of space between the quasar and us. So the interpretation of this is that there's neutral gas, hydrogen, that's absorbing the light in this part of space. And that is intensely interesting because quasars, which are closer, don't show that. They don't show zero. They show a step there, but they don't show zero. And that means that the gas is ionized. It's transparent, ionized. So the universe made a switch from being mostly ionized to being mostly neutral here. And we're trying to understand that because we want to know what did it. What was the thing that made the gas in the intergalactic medium ionized? Okay, I want to tell you a few more things here. One is that we don't just do extragalactic astronomy, and the other is how to get at the data and how to have your students get at the data. so I'm getting close to the end. This is a picture that is very contrast enhanced of a globular cluster. This is a globular cluster called Palomar 5. It's a rather unspectacular looking cluster. It's not like M15 or M13. Where the stars that are likely to be associated with this cluster, given its distance, given the type of stars it has, we've gone into the entire database of however many stars in this huge area of stuff to sort of filter out those stars that are most likely to be part of Palomar 5, and then get rid of everything else and turn up the contrast. Okay, so what you see here are these things that we call tidal tails. Okay, so these are okay. That was probably not very clear. Okay,
They're called what?
This blob here is a contour plot of representing the number of stars in that direction. Okay, so you're not saying individual stars, but that's the idea, that there are more stars here and fewer stars over here. Okay, and this is a normal. You're right, tidal tail. Okay, and this picture, this is I perhaps should have shown you this picture to start with. This is the idea. Here's a globular cluster. Okay, it has a certain orbit around the galaxy, the Milky Way, just like any globular cluster has a certain orbit around the galaxy. And so we can predict where it will go and when it will go through the plane of the Milky Way. Every time it passes through the plane of the Milky Way, it experiences a stronger gravitational field. Okay, when it does that, it gets pumped. So the gravitational energy gets sort of pumped into the cluster. And depending on the details of the dynamics of the orbit, it can start to disintegrate. Okay? In other words, tides, essentially the Milky Way, think of it this way, the Milky Way is raising tides of the stars in this cluster, and it's pulling it out. And so we can, by studying the specifics of this trail, I don't know which way is the leading direction and which way is the trailing direction, but whichever way it is, by studying the details of this, we can figure out what the orbit is, and thereby get a handle on.
So they're stretched out along the original orbit.
Yeah, that's right. That was a 10-degree slice. No one's ever seen anything as long as that before. There's sort of hints of this in some other systems. But what the physics we're trying to get at is how the distribution of matter is how dark matter is distributed in the Milky Way. Okay, let me skip some of these things. You'll see much more of these this afternoon. Here's another thing that's kind of fun. This is a gravitational lens. Okay, there's a galaxy that you can't see very well here because of the contrast, and there's a more distant quasar behind the galaxy. So since light is bent by gravity, what happens in this case is that we can get multiple images of the same quasar because there are different paths that the light can take that can come around the galaxy, all of which are provide an image.
And you know they're the same by looking at the spectrum.
Yes, you take a spectrum of each one of these and they're identical. So what this plot is you say, okay, let me model this dot here, this dot here, and this dot here by the same model of what we call point spread function, and subtract it out. So that's been subtracted, that's been subtracted, that's been subtracted. And this is a way to see the galaxy, which would otherwise be not visible because of the contrast. So this is another rare object. Very few of these have been found, and we were able to find one. This is actually not our image because this is from a telescope in Chile called the Magellan telescope, which has better image quality, but we discovered it. Okay, so this is the last science picture. It's complicated, but that's part of the story. It's the richness of information that we have. These are the asteroids that we have, or at least some of them, 6,000 or so. That's about 10% of the asteroids that we've discovered. But these happen to be the asteroids that have that have orbits that were already determined by other studies, by other surveys. So we know the orbital elements of all of these asteroids. Therefore, we can plot the distance from the sun in astronomical units, and we can plot the inclination angle with respect to the ecliptic. Okay? And what you see here is, of course, this is already known because the orbits were already known. This plot could have been made before. What you see are it's a huge amount of structure here. There are gaps. There are certain places where there aren't any asteroids because of the solar system dynamics cleaning out those particular regions. Let's see. So Mars is somewhere out here. What's the
1.5?
1.5. Okay. Mars is here. My laser is getting flaky. Jupiter is out at 5. This is the main asteroid belt. Well, what this plot shows you, which no one had seen before, is that what we can measure is the colors of the asteroids very accurately, because we have these beautiful 5 filters, very excellent, calibrated, and we can then overlay some information about the color of the asteroid on this plot. And what it shows is that there are corresponding groupings of color as well as that correlate with dynamics. Okay, so that is not a trivial point. There's no obvious reason why dynamics and presumably color is something about the surface. Obviously, the color has something to do with the surface characteristics of the asteroid. And this is saying that they're correlated.
So possibly chemical composition.
Yeah, chemical composition and other or physical characteristics of the surface. So we think that these are born in families, that asteroids come in families, so that and of course a family would have correspondingly similar orbits and similar chemical and physical characteristics.
Okay, see if we can find the ones in the lead cold.
Yeah. Yes. Okay, or platinums. Let's see. Okay, now I'm going to switch topics. I'm going to tell you a little bit about how to get at the data. This is a little bit changing, and Cristobal might know more than I do about this, but what I can show you now, because it's what we have currently, and we're now working on a new release of data that may have bigger and better things. But essentially, there's this thing here is our public outreach, or school outreach, or non-professional astronomer outreach thing that we call the Sky Server. It has lots of goodies on it. It has, you can look at pictures of the sky. You can look at individual objects. In other words, if you have the coordinates, an object, you can enter it in and it will come back. And you can ask, say, give me all quasars, in this part of the sky, or all quasars with a redshift of 1.5, 1.6, or something like that. And the query comes back, and you can then load it up into Excel and make plots and stuff like that. So you need to know, to do an HR diagram, you need to know the luminosity of the star. To know the luminosity of the star, you need to know its distance. But we don't give you the distance. So you will have to figure out the distance on your own. But having said that, then yes, you can do an HR diagram. If you got a cluster, you can do an HR diagram. And the rest of these slides are just give you a little bit more of a flavor for this. So you can search by RA deck. It gets a little bit arcane, but you get a chunk of information that has to do with the imaging. For example, what the magnitudes are. These are the magnitudes. Okay, what the reddening is, that sort of thing. There's just an unbelievable amount of information for each one of these things that we derive from our data. And then down here, what I can show you is the spectroscopic information. So here's the redshift here, and other good stuff. Here's the spectrum. You can download the GET file, and there's another tool called SCSS cutout, and this is the sort of thing that this is in a state of flux right now. I don't know what manifestation of this will actually be available in the next few months. But it'll be something like this, and you can make a map of the sky. This one tells you of all the objects, which ones we have data, which ones appear in our database. So, for example, the red diamonds have a spectrum. So, if you have a picture of the sky, this will tell you all the objects that have a spectrum in our database. Okay. Yeah.
What the dark matter is that have anything with structure?
Would you back up once?
Yeah.
Thanks.
Yeah. So one of the sort of the definition of dark matter is this matter which does not interact with ordinary matter. In particular, it doesn't interact with light or doesn't produce light.
Okay.
So we know it's there because it gravitates. We know it's there, but there is too much gravity for us to account for by ordinary rocks and stars and such. So the short answer is no. We don't have a spectrum of dark matter.
A light spectrum. But
Yeah.
is there some sort of electromagnetic
No.
waves or
No, there's no interaction of electromagnetic waves other than by gravity. So for example, light would be bent gravitationally by a lump of dark matter. So one of the things we can do is study gravitational lensing. I just briefly mentioned that as a way to get another handle. Okay. All right. This is what will happen I hope in February. If we can. This is what the project is intensely working on right now, is making the first data release of DR1. I hope in February, a huge amount of area of sky and a huge number of specs. This will keep you busy. Okay. This is the main website, and everything will be linked to the main website for the survey.